Now, the big question is why palladium in catalysis, specifically widely used in homogeneous catalysis. This actually shows that designing palladium, like adding ligands to palladium, actually plays a role in making it to be soluble in various aqueous solutions, and the aqueous solution must contain a specific substrate that will be instrumental in getting our right products. So why palladium is special is due to what we see in the academics and industrial laboratories, how widely used in chemistry, and also how it actually gears towards regioselectivity and chemoselectivity of our organic products. Now, the right palladium means how can we pick the right palladium to create the right organic products, and based on various laboratories and also industrial experiences, they actually noticed that it exists as palladium 0 and palladium 2, which means that if you do the d electron count, palladium 0 has 10 electrons in the d orbital, while palladium 2 actually has 8 electrons in its d orbitals. Now, based on the two types of palladiums here, we actually notice that designing palladium with the right ligands actually shows that the well-known species for palladium 0 is actually this particular species on the left side, which is called a trace dibenzylidene acetone dipalladium 0 chloroform complex, which is what we have right here, while on the other side we actually have a palladium 2 plus that actually is well known to be called bisphosphine palladium 2 chloride. And what you see here comparing the left side from the right side is not actually noticeable until you perform various reactions. First off, we actually determine the left side by experiment that it's actually air stable, and on the other side is also air stable. Now, palladium 2 plus is widely used than palladium 0, and it's quite fascinating that is actually the case. So most research groups, they are able to actually purchase this particular form of palladium rather than the palladium 0's species right there, but it's quite expensive to actually get. So based on what we notice now, that okay, we actually use palladium 2 plus in a lot of chemical reactions than palladium 0, how can we be able to convert palladium 0 to palladium 2 plus? So basic chemistry shows that, oh, first off, we have the oxidation states. There are actually two possible ones. We have palladium 0 and we have palladium 2. That means that palladium 0 has a charge of 0, which is neutral, and palladium 2 has a charge of +2. The big question is, what redox reaction is happening to go from 0 to +2? This particular redox reaction is actually called oxidation, and through oxidation, which is by losing 2 electrons, palladium 0 can achieve a palladium charge of +2, and in order for we to do just that, we actually add a specific substrate that will be able to accomplish that, and this substrate is actually called an organic halide. So using organic halide, we'll be able to convert this electron rich palladium that has a coordinatively unsaturated design complex in order for it to go from palladium 0 to palladium 2. If it has a complex that is coordinatively saturated, this particular process will not take place from going from palladium 0 to palladium 2 plus. And in order for we to be able to achieve a coordinatively unsaturated complex of palladium 0, we use a particular reaction step called a ligand migration, which we talked about on our previous video. So now this is actually out of the way, let's look at the road to oxidative addition, since you already know that we need to be able to convert palladium 0 to palladium 2+ through oxidation. So using an organic halide, we need to be able to achieve this particular desired form of palladium. First step is through series of ligand migration or elimination. So first up is we actually lose the first ligand, and what happens is that we have one ligand, but now this complex, which has 18 electrons, now comes down to 16 electrons, knowing fully well that this palladium has a charge of 0. When we move from the second species to the third one, which is right here, we lose another ligand, and what happens as a result of that is that we actually have a complex now that has 14 electrons. 14 electrons in total in this complex shows that this particular complex is really reactive, and once it's reactive, once it sees any organohalide, like for example, we just put R1 attached to X, where X is actually a halogen, which I'll put as halo, or this particular species right here, organohalide actually performs a reaction called oxidative addition, and what happens then is that we actually form this particular product right there, and they are cis to each other. Since we've created this particular species, what we notice is that this particular sigma bond here is highly reactive to any pi bond that approaches this particular complex that is formed. Once you notice that this sigma bond is created, the next step is called migratory insertion, where we have this particular alkene coming in contact with our complex, and what we get as a result is the formation of a pi complex, where on this side we have our R group, which is R2, and by a particular type of migratory insertion called carbopalladation, where we have the carbon palladium bond actually formed between a particular pi bond that is existing in alkene, we actually have this particular reaction where this R group migrates over to this side, and then this particular pi bond forms a sigma bond with our palladium, and what results in is the formation of this particular alkene metal complex. And taking note of this, we actually notice that this particular complex that's formed is unsaturated, and to make it to be saturated, we introduce our ligand, which comes in contact with this, and then we have our L, and here we have our X, and right here we have our other alkene. Once you notice what you've actually created, we see that this palladium here has a charge still of 2, and it is a 16 electron complex. So based on what we've actually accomplished, we notice that in ferrous metals, they actually continue in this olefin and insertion process that creates polymers, but for palladium that is not the case. So what happens instead is that this palladium has the L ligand positioned right there, and on the other side we have our R1, and here we have our R2. You notice there is a hydrogen right there. Due to the process called a beta hydride elimination, what happens is that our hydrogen here actually migrates over to this particular palladium center, while this particular bond cleaves and forms a pi bond, and what happens as a result is that we have our beta hydride elimination that results in the formation of our product, and we have other side of the product. And taking note of that, we actually know that this has 16 electrons, and this palladium still has a charge of +2. The one that is coming from it actually has 16 electrons with a palladium of +2 charge. Enough for we to regenerate our 14 electron reactive form of our palladium that will be important in recreating more of this particular product. We actually add a base, and what happens is that this base that is added will actually remove the hydrogen and the X, which results in the formation of a 14 electron reactive that will be then used again for the same reactions right there. That's about it for this particular video. Hope you're able to understand this fantastic property of palladium and how it's actually used in various types of homogeneous catalysis. All the same, stay smart and believe in yourselves.